Okay, but maybe other participants will join us, and in any case, we produce records of our meetings. So we start our usual open meeting of the Academic Council of the Faculty of Computer Science. The schedule is, as always, 20 minutes for talk and 10 minutes for discussions. And our first speaker is Bruno Bauwens. So, Bruno, you are welcome.
Okay, thank you. I had a bunch of practical problems last 2 days because my computer broke and my backup was in Belgium. So I apologize for only preparing half of the talk, but we won't have time for the last half anyway. So, okay, so here is the outline. I will speak about points 1 and 2. I have a different presentation with points 3 and 4 in case there is time. So I will speak about data compression, and I will present a new result, a result that's kind of expected, and many special cases have been known, but we managed to prove a very general and clean statement. Then I will present, with this clean statement, we can analyze many applications in a much more cleaner way, and so there is progress in many places. And so there is a bunch of papers, and I'm very proud that one of the papers was accepted in Journal of ACM, and my co-authors tell me this is very good journal. Okay, so I will present the main result. It's one slide. Then I will present why it's optimal. And then I will speak about 3 applications. So distributed compression, secret key generation, and error correcting code. And then if time permits, I can probably quickly say something about points 3 and 4. Okay, so let's go to the problem. So problem is about data compression algorithms. And data compression is done by 2 algorithms, a compressor that takes a file and makes it smaller, and a decompressor that makes it bigger. And so we are interested in 3 parameters. What's the compression size? How fast is a compressor? And how fast is decompressor? And so it would be nice to have compression and polynomial time, decompression and polynomial time, and having smallest compression size in terms of Kolmogorov complexity. But these 3 things together are not possible. So our first, so we will be interested in optimal compression. So that means optimal compression where we reach Kolmogorov complexity. And our main result stands that we can achieve optimal compression and polynomial time, which is a bit of counterintuitive result. But for people who know about hash functions, this might be somehow expected. So note that we do not care about decompression time. So of the 3 criteria, we want optimal compressed size, we want fast compression, but we need to drop one of the 3. We will drop decompression time. And so for this reason, results will not be practical. Decompression time will be exponential. So, for example, if you brute force hash codes, you will go over the whole list of your whole list, and this takes exponential time when you consider strings of length n. Okay, let's give a bit more details. So what is the notion of optimality that we use here? So given a decompressor, the optimal notion of, so for now, let us think that D equals D prime in this definition. So given a decompressor D, then the natural notion of optimality is just we want to find a program that the shortest program that the decompressor expands to the original file X. So, okay, we will relax this a little bit. So given a compressor D, we allow to look at a different decompressor that might be a bit slower. This different D prime compressor should decompress the program, and it should use a program of length K, which is the optimal. So I hope you can see the pointer. So here you see the Kolmogorov complexity of compressor D. It's the minimal length of a program that produces X. And we want to achieve a program of length K, which is close to this minimal length plus some delta. So that's what you want to achieve. And so this target length K will be an extra input of the compressor. I will later explain that this is unavoidable to get such a general result. Okay, so this is our notion of optimality. We will use a compression algorithm that's probabilistic and with large probability, say the error probability 1%, there can be any epsilon. We want to recover the original file X. So this is our notion of optimality. So we say compressor C is delta optimal for D if compression sizes of our system, compressor and decompressor system, is the Kolmogorov complexity with compressor D plus some small delta. And so here is the first result, which is new. It says that there exists a computable compressor that is optimal up to logarithmic term for all decompressors. So there is remarkable because there is a single compressor that is optimal for all decompressors. The second result says that there exists such a compressor that works in polynomial time. So here optimality is a bit weaker. The optimality factor is a bit weaker. It's log K, log length of X. Okay, so now let us look at the first theorem that is computable, and let us see why it's remarkable. So, okay, so first of all, D prime is very slow. I already told this, but it's somehow effective. So if we have oracle access to compressor D, then we can evaluate D prime for a program that computes a string of length n in space poly n. So it's not completely hopeless, but it requires exponential time. So, okay, let us go to the necessity of assumption. But let us first look at this theorem and let us think where can we improve this theorem. So maybe somebody can say something. So where do you want to improve this theorem?
I would say a remark. It's nice to get the same what you want with high probability, but would be also nice to have a guarantee that there's something you output is close with respect to some measure to X. Even if it is not X, then maybe it's close.
Yeah. That's very good suggestion. Let's dream even more. Let us have this result with deterministic compressor. That would be even better.
Yeah.
Okay, actually, it's very good research question. So thank you. I didn't think in this direction. But first requirement, can we make C deterministic? So maybe there are other things we can improve in this result. So theorem has one numerical quality. It is order log length of X optimal. Can we have 0 optimal? So it's perfectly optimal, or O of 1 optimal. So that's the second thing. And the third thing, now I forgot myself. What's the third thing we need to improve? So get rid of K, make it deterministic. That's 3 already. So get rid of K, make it deterministic, and decrease delta.
I'm sorry, just understanding of this definition. Sorry for a stupid question, but I don't see the relationship of D and D prime. What's the relation?
Okay, so you give me your favorite decompressor D.
Yeah.
So you invented, so you made your compression algorithm C and decompression pair, compressor, decompressor. And we will ignore your compressor. We will only look at your decompressor.
Yeah.
And then I will say that this special compressor from the theorem is almost as good in terms of compression length. But the problem is that we need to change a little bit your decompressor. And so that's the role of D prime. So we cannot compute exactly the same programs. We need to change the program a little bit. But we promise that the code length will be essentially as small as your best code length.
Okay, thank you.
So that's intuition. Okay, it's a very important point. Are there more questions about this point? Okay, so now let us look to the 3 questions about optimality. So, and for this, we will look to a very to a special type of compressor, which is just called optimal Turing machine or standard Turing machine for convenience. So standard Turing machine means that we can simulate any Turing machine by prepending some fixed string to the program. And so for such a machine, this Kolmogorov complexity function that you see here is minimal up to an additive constant. And so programs from any other machine can be simulated, but their length increases by constant. Okay, and so if we look at the special case of previous theorem, for such Kolmogorov complexity function, we get corollary here. And so this is remarkable because for this machine, we get some, the function Kolmogorov complexity is not computable. But if we tell our compressor this uncomputable information, then suddenly the shortest program itself becomes computable. And so this is kind of unexpected. Yes, and I actually, there were, I found a teacher who even teach this result in his class about computational complexity. Okay, so let us now go back. So why do we need the target size k? If we don't give the target size k, then we can read out Kolmogorov complexity from the generated length of the length of the generated program. And so the ck. So if compressor C doesn't know k, then length of C of x is close to Kolmogorov complexity of x. That means C computes Kolmogorov complexity. It's impossible. So we need to tell it something. The second thing, and now the 2 other things, can we decrease delta? And that follows from this proposition. So for any delta optimal compressor, we have delta is at least log n minus log n, where n is the length of the input string. So if delta is a function of n, then this bound holds. So we cannot go, we can only improve the theorem, the delta in the theorem by constant factors. So recall we had order log n. Okay, and for randomness, there is also a lower bound. We can do it with fewer randomness, but then we need to sacrifice on delta, and this is the right one in the bottom. Okay, so now let us go to applications. I will discuss 3 applications. Okay, there are 3 minutes left. First one is document exchange problem. And so let us, it's kind of absurd situation, but let us try to think about it. So imagine a teacher wants to give a lecture, it takes 1 hour, 60 minutes. But all students know already half of the lecture. So there are many parts in the lecture. All students know some parts, but all students know different parts. Can the teacher still give a 30-minute lecture so that all students can recover the full lecture? And so in computer science, there is something that says Slepian-Wolf theorem. It is possible. says computer science, but student will need to compute something complicated. So in practice, it's not possible. But theoretically, it is possible. And so here we have a more general setting. So we have two strings, x and 1, two different sources. The source that has x1 doesn't know x2, and the source that has x2 doesn't know x1. And they can send a message. First source k1, second source k2, and they send it to a common receiver who then needs to reconstruct x1 and x2. So connection with previous example, x1 is the full lecture, x2 might be what the student already knows, and k2 is infinity because we don't restrict k2. Okay, so but let us look back to the scheme, and we see that Kolmogorov complexity of x1 and x2, it's necessary that it needs to be smaller than k1 plus k2, because initially the receiver knows nothing, and after receiving the messages, he knows the pair x1 and x2. So it's definitely this first condition is necessary. Second condition is also needed. If receiver already knows x2, then the message from the second source is no longer informative, but then he needs to understand x1. And so we look to the information in x1 given x2. It's Kolmogorov complexity of x1, where we consider programs that x2 have as additional input. And similar for the third condition. So, and it turns out that these three conditions are not only necessary to solve this problem, they're also sufficient. And so this was discovered by Slepian and Wolf in 1973, but they gave Shannon entropy version. And then 2005, Romashenko gave Kolmogorov complexity version, but here the programs, they could not be computed. So essentially they could not be computed, and moreover, to recover the pair x1 and x2 from the programs, additional advice was needed. And so in our paper, we obtain polynomial time compression, and no helper bits are needed for decompression. But again, decompression is exponentially slow. Know that this problem is a huge research problem. For example, when webcams, if several webcams look at the same object, they want to send their images in compressed form, but when they look at the same object, their messages are somehow correlated. So you could use such algorithms in practice that save bandwidth. Okay, and so what we also did is generalize this to a large number of sources. And so here we need some more complex condition. We need that for every subset of strings. So as sources, each have their own string and each have their own bandwidth. And we need that for every subset of strings on the left, the total bandwidth of these sources should be at most the complexity it should be at least the complexity of these strings given the other strings. So that's clear necessary condition. And it turns out that this is essentially a sufficient condition. And so the equation, the assumption in the theorem has ki minus logarithm over number of sources s divided by some epsilon, which is error probability, minus the delta. And the nice thing is that any compressor that is delta optimal for compressor U can be used. Okay, and so then reconstruction happens with probability 1 minus 8 epsilon s. And so we need to decrease s. We need to decrease epsilon by a factor 1 over s to have reasonable probability. But in the assumption, the dependence is logarithmic on s. So previously, so Marius had an older result that was published in Stock conference, where he had double exponential dependency on s. So there, I made double exponential improvement. Okay, so there is no hope to get such a precise result, using Shannon version because of statistical fluctuations. Okay, there are two more applications, but they're just small slides. So this application is due to Marius Simand, and it is kind of first operational characterization of mutual information. So here the problem is that two sources, Alice and Bob, needs to generate a secret key over a public channel. So secret key for encryption purposes, for example. And so easiest is if Alice and Bob meet in person, flip some random coins, and then they have a secret key for arbitrarily long encryption. However, if they don't have this chance, then they might use a file. Alice might have a file X, Bob might have a file Y that's different, but it needs to have some correlation. And then they can generate a secret key that's equal to the mutual information. So what is mutual information? You see it inside the theorem. Here is the definition of mutual information of X and Y. And so using this algorithm, what can happen is that Alice can send the string X to Bob using a minimal amount of information. And it turns out that this information is random for a person, that this information is random relative to X. And that means that an observer will only see Tx, which is independent of the information that's shared between X and Y. Okay, this is not so easy to understand. But basically the algorithm just presented before can be plugged in this result. And this is also the main result that was accepted for publication in the Journal of the ACM. Okay, and this is optimal. And okay, it's first kind of operational style characterization of mutual information. Okay, the third is about error correcting codes. It's just one slide, but I think it's a bit difficult to summarize. So what here we have done is that we have constructed error correcting codes that work against any channel. So that normally error correcting codes, they are created for a specific type of attack. And here we managed to have error correcting codes that work for any type of attack under a very broad class of attacks that contain bit flip, bit erase, no, not bit erasure. Just a general class, and but the price is that shared randomness is needed. So that means encoder and decoder needs to have shared randomness plus the adversary who chooses the attack. So it's not a statistical, but an adversarial result. Adversary cannot see the shared randomness. And so the probability is taken over the shared randomness in this definition, in this result. So correct recovery. An algorithm that does this is essentially the same as previous algorithm, but we use a special combinatorial construction from a different paper that has some linearity properties. Okay, I will stop here because I went over time already.
Okay, thank you very much, because really time is running. So dear colleagues, do you have any questions, comments? Something related in your works?
So Dennis has
something related to my work. Yeah, coming from mathematical heaven to close to Earth, there's sort of practical analog of Kolmogorov complexity called minimal description length. Do you think these results can be rewritten, reformulated in terms of minimal description length?
So yes, it connects to your previous argument where you say, I want to have some output that's somehow close. So these minimum description lengths, they are interesting for noise removal. Okay.
Yeah.
So you split your code into two parts, a model part and another part that looks like noise, and then you can save bandwidth on transmission by avoiding noise. It's a very good question. So all techniques are orthogonal to this. So this is more combinatorial in nature. And what you asked for, actually, I wrote a grant application where I had a special plan for exploiting such things, but I didn't do anything of this. I did other things. So the grant has enough papers, but it's an excellent question.
Thank you. Thank you for your very deep talk.
Okay, do we have any more questions, comments? If not, then I would like to thank to Bruno for his excellent talk. And we are ready to start the second talk by Quentin Parry.
So my talk is going to be a bit less technical than that of Bruno, in the sense because I actually targeted this talk for people that are absolutely not familiar with this field of research, and so the online learning I'm referring to is a subfield of learning theory, which is not about learning through Zoom, but rather learning through a repeated game. So the plan of my talk is going to cover, actually, for the most parts, some background for people to understand the field, and to start understanding the research I am personally interested in, and give a flavor of the results we've obtained with my PhD student. So I'm going to start by a brief description of what is a special problem in the field of online learning. So the field of online learning is a very vast field of research, and I'm going to concentrate on one abstract framework, which is known as online convex optimization. So how can we present and understand this field? So usually to present this field, we need two essential ingredients and nothing else. So we need a so-called decision space, which is a convex subset of R to the power D, hence the classical Euclidean framework. And the second, we need a family, capital F, of convex functions defined on this decision space that we call the loss class. So these are two things that are given to a player before the game starts, and then the player or the learner is playing the following repeated game against what we could call the environment. So at every time step t, so t refers to here a discrete time. So the player selects a point in the decision space. So he takes his decision, and once he commits to his decision, the environment reveals a loss function ft in this loss class, and once this function is revealed, the player incurs the loss ft of xt and moves on to the next round. So it's very easy. The player picks a point. Once the point is picked, the environment reveals a function, and the player pays the price ft of xt. Okay. So in this game, what's the goal? So there's many ways to frame the problem, and the typical objective, which is studied in this setting, is to minimize the so-called regret. So this notion or this performance measure actually encodes two things. First of all, it encodes the cumulative loss of the player after n rounds, so the amount the player pays after n rounds of this game. And then, because as in most of learning or game theory, there's a competitive benchmark that one is taking as to define performance. And in this case, the simplest possible benchmark, the one I'm going to focus on today, is the best cumulative loss in hindsight of a fixed strategy. So this might seem a little bit unambitious at first sight as a competitive benchmark, but it has some interesting connections to offline or classical convex optimization, statistical learning theory, and game theory. So I will just stick with this for the short talk I'm going to consider. Okay, so I'm going to briefly present maybe the two most basic possible algorithms that one would study in looking at this problem. The first one that I'm not going to consider much, but at least going to give a flavor of the type of problems we get when we leave the Euclidean world, is the so-called online gradient descent, which was proposed by Zienkiewicz in 2003. So as you see, the problem is the algorithm is extremely simple. It suggests to pick an initialization at time 1, and then at every time step take a decision, which is the previous decision from which we move in the direction of the opposite of the gradient of the loss observed at the previous time. That we reproject on the convex set K. To remain in the decision space. So it obviously looks, a lot as typical projected gradient descent. Fine, with the only difference that the function whose gradient we're following changes with time, which is if you've never seen this before, should surprise you and should actually raise the question, why is this working at all? Because you're not performing gradient descent on a fixed function. You're actually following the gradients of functions that change over time. So it seems a little strange. But actually, there's a deep reason why this works, which has to do with the robustness of classical gradient descent. And it was shown by Zienkiewicz that actually this provides some reasonable performance in terms of this notion of regret that I presented previously. So maybe I'm gonna present two types of results which are available in the literature. So the first one, which was given by Zienkiewicz, actually says the following: so if every loss function in the loss class has a bounded gradient function, and if the decision space has a finite diameter. So these two bounds G and D being known. So obviously this is a big drawback of this algorithm, but I'm just presenting the simplest possible version. Then, given these two facts, a relevant choice of the smoothing parameter allows to derive a bound on this regret that is of order square root of n. So the fact that this is sublinear, so without getting into details, the fact that the bound that we get, or that the regret itself is guaranteed to be sublinear, meaning that divided by n, this tends to 0, actually encodes the fact that, or shows that we are actually really learning something along the way, and not just guessing at random. So this result has been improved. In 2007, showing that under slightly stricter conditions, meaning that all loss functions are not only convex but strongly convex, which means that in the world of differentiable functions, this would just mean that the Hessian matrix has eigenvalues lower bounded by alpha. Then an appropriate choice of the smoothing parameter yields an even better performance guarantee of order log n for this regret. So fine, this is a very short overview of what you could say, for instance, for this very simple algorithm. So another algorithm, that is, so maybe just, a final word about this algorithm. So it's obviously a basing block in many improvements and refinements of online convex optimization algorithms. But for what we're the purposes of this talk, one observation is that if you look at the construction of this algorithm, it relies heavily on the Euclidean structure of the problem in many respects. The algebraic definition of the point inside the projection, the definition of the gradients, everything really depends on the availability of Euclidean structure. So how to possibly change or adapt an algorithm in the context where we don't have this nice Euclidean structure. So before answering these questions, I'm going to talk about...
May I ask, what is a projection, proj K?
Yeah, so it's the closest point inside of the set. So proj of... so it's the point that realizes the distance to the set K. So
okay, thank you.
So if you have your set K, a point Z, proj, this would be...
okay, thank you.
Proj K of Z. So obviously, you're pointing towards something which is really important, is that to implement this algorithm in practice, you have to compute this projection. And for some types of convex sets K, this is a trivial computation, and for other convex sets, it is a highly intensive computational problem. And sometimes it's even so intensive that you might want to think of another algorithm. So that's a good point. Thank you. Okay, so let me talk about the second algorithm, which is the one that has been of more direct interest to my PhD student and myself in this research, which is the so-called exponentially weighted average, which is equally standard in terms of algorithm. This was also one of the first algorithms that you can talk about because it requires very little background, and it's the following. So it supposes, it says it requires to initialize a certain measure, probability measure over the decision space K that is initialized at the uniform measure over K. So this obviously first, if you're looking for a non-Euclidean generalization of the algorithm, this already should, this is already bad news. You cannot define the uniform measure on anything. I mean, in some Riemannian manifolds, it's and something which is essentially included in a Euclidean space or embedded in a Euclidean space, you can come up with constructions or generalizations, but in metric spaces which are not of this nature, it's more complicated. But we'll come to this. And then once you've initialized your measure M1 to being the uniform measure, you select for every time step t, xt, so the decision of the play, to be the average of this measure mt. So in probabilistic terms, obviously this is simply this is saying the expectation, of course, of capital X following the measure mt of a random variable X. Okay, and then you update your measure mt plus 1 to being the measure with density up to a normalizing constant. So this is just a normalizing constant, to be the measure with density exponentially minus beta ft times the previous probability measure. So this has several interesting properties. So by construction, if you look at this update, it naturally emphasizes with time the role of points with small cumulative loss. Okay, so because you're multiplying by something which is obviously small if ft is large, fine. So maybe, let me check what was our, okay, yeah. So nt was just a normalizing constant. And as we'll discuss later on, what's interesting here, even though the formulation of this algorithm poses some difficulties, it has the nice feature of involving only first order information on the loss functions, ft, meaning we don't need to compute gradients, but just the values of the function f is enough. And this, for generalizations in spaces where computing gradients is not obvious, is attractive. Okay, so just a comment on the classical analysis that can be made in the Euclidean space for comparison with our results. We have this result, so many more are possible, but I will state only one. So if the set K is a convex body, so convex body here means non-empty, a closed convex set with non-empty interior, essentially just conditions that allow to define the uniform measure over K. And supposing that the function f, all the function f in the loss class are beta x concave, which in terms of gradients can be defined as saying that the tensor product of the gradient of f with itself is lower bounded by beta times the identity matrix. Or more simply, let me make a comment here. Or more generally, actually, when f is not differentiable, this is simply saying that the function exponential minus beta f is concave. So this requirement is actually asking a little bit more than convexity, and in the sense that we can show that any beta x concave function is convex, but it is also a little bit less than strong convexity. So it's somehow a mild strengthening of this requirement of convexity. So under this requirement, what we can show is that this, without any other requirement, this exponential weighted average with parameter beta gives a regret of order log n, which again implies that we're learning at a rate which is rather fast. Okay. Just a few comments to summarize on this algorithm. So on the plus side, it requires zero order information on ft, so just the values of f and not the gradients. It achieves a log n regret with comparatively less assumptions than online gradient descent. That to achieve log n regret requires more convexity, so it requires strong convexity, and does not require a boundedness of gradients, which is also quite important. I didn't write it down. So on the negative side, it is computationally harder than online gradient descent, because you see that the computation of this integral is not a trivial problem. So it has to be accounted for. And it also relies heavily on the Euclidean nature of the problem, because of the way the integral is constructed. It requires the measure mt to be to live on at least maybe the most general definition of integral that one can come up with in the math course would be the Bochner or Pettis integral, which is defined on a Hilbert or Banach space, but it's a hard construction, and outside of this setup, it's hard to see what we can come up with to generalize this construction. So I'm gonna provide one motivation for why would we ever want to leave the non-Euclidean setting. It's not just for the love of generality and abstractness. It is because we would like to do online learning in spaces which are relevant for applications, but that are definitely not Euclidean. So one of the maybe more fashionable spaces nowadays in applications is the so-called two Wasserstein space or two Kantorowicz space, which is the space of probability distributions over the set RD. Okay, so denoted P2 of RD, so with a weak requirement that they are square integrable, so you can define the variance of this probability of these probability measures. And so it is called the 2 Kantorovich space whenever it is endowed with a very specific metric, which is the Kantorovich 2 metric, W2, defined by this complicated formula, where so the W2 between mu and nu is defined as the infimum over all couplings of these two distributions of the integral of x minus y to Euclidean squared integrated over the coupling. So a coupling, for those who are not familiar with this thing, is simply a probability distribution over the product space, RD times RD, where the first marginal is mu and the second marginal is nu. So why is this? So why is this space of specific interests for people in the machine learning community? For instance, it's of interest for many people outside the machine learning community, but for those who are in this community, it has been attracted attention for several reasons. First, it happens to better encode the geometry of some problems in some cases. So it's not a magic tool that works for every possible application, but it has been for many applications shown to be relevant. This is mainly, for instance, due to some works of Facundo Memoli. And it's also has become a computationally attractive thing due to the recent breakthroughs in computational optimal transport. And basically, this means the possibility of computing such distances between probability measures, which was a hard problem before recent breakthroughs. So to maybe give a feeling of what I mean by this first statement, that it better encodes the geometry of some problems in some cases, which is a very vague statement, I just want to give you a very toy example that, in my opinion, actually shows really why you would want to consider this space rather than another one. So suppose you consider...
Quentin, can you say what is the book on the previous slide of Perre?
Yes. So Perre, so it's by Gabriel Perre and Marco Cuturi.
Okay,
and
thanks.
It's freely available on Archive, and it's called Computational Optimal Transport. So,
okay, thanks.
It's a very good reference because they update it every week almost, and it's very up to date. So the guys are doing a great job. Okay, so I just want to give you a very so stupid or simplistic feeling of the difference that you have between or the interest of this the geometry encoded by the Wasserstein or the Kantorovich space. So look at these two images here. So here, on the two squares with the black dots are just represent images, okay, black and white images with two dots on it. So there's two ways to look at this problem or encode this object from application perspective. You can either, in a maybe more classical approach, consider this to be a matrix of pixels, where each pixel is attributed a number between 0 and 1. 0 being white and 1 being black, and everything in between being a gray level of gray. Okay, so with this representation of the object black and white image, the natural structure that comes with it is that of is a Euclidean structure of matrices of I don't know, n by m pixels. So given this representation, if I'm asking you to draw the shortest line between these two images, how would the elements on this line would look like? So the shortest path in a space in which you can talk about continuous path is what we call a geodesic, and in the Euclidean representation, this is how it would look like. Okay, you just take every pixel and you just you take the 1 minus t times the value of, I think it's clear for everyone what I mean. So there's nothing wrong with that. It's fine if you decide to model your problem this way. But in this case, the middle image, if you want, that you get is this one. Sometimes it might be what you're looking for. Sometimes it's not. So without getting into details, what I want to show you now is how the geodesic looks whenever you endow the space of probability measures whenever you look at an image as rather than a matrix as a probability measure over the square, okay, and when you endow this space of probability measures with the Wasserstein or Kantorowicz 2 metric, this is the geodesic you get. So there's nothing better than the other, but it might be the case that this encodes more the structure that you're looking for. So people have been, so this is a baby observation that has been generalized in many cases, where instead of black dots, people look at faces, and they try to interpolate between two faces, and the Euclidean geometry would provide you with an image which is blurry. While if you look at the geodesic between two faces in the space, in the Kantorowicz space, you obtain something that looks like a face along the geodesic. So people have been playing with this a lot. Okay, so hopefully this actually gives you a kind of a very vague feeling of why we would, for applications, look at this type of abstract framing. So now I want to give you some, very quickly, because I think my time is almost over, some elements of how to deal with the problem and generalizing this, the last algorithm I presented, which is exponential weighted average, in an abstract metric setup, and show you the type of results we can show in connections with interesting things that I personally was not expecting. So to define, so I need to define now what is called a barycenter in a metric space that will play the role of averages when you cannot average in the traditional sense. So for this, you just need an abstract metric space and a probability measure over M. And you define a barycenter of measure M as any point X star. So a barycenter, by the way, is also called a Fréchet mean. Any point X star that minimizes this quantity, which is sometimes denoted var of M at X. So it's the variance functional of the probability measure M over or the variance functional of the distribution M. Okay, so several remarks. There are very interesting questions from a mathematical perspective that have been intensely studied by myself as well and colleagues related to the existence of these objects, their uniqueness, statistical properties, approximation, computation. So the field of study around these objects in metric spaces which are non-Euclidean has been really intense, but I will not talk about it. It suffices to say that it's interesting. It's a natural object because whenever M is Euclidean and D is the Euclidean distance, well, the barycenter reduces to being exactly the average. So it's a nice exercise to give to students. That to show that the expectation of a random variable minimizes this variance functional. So it's a relevant generalization. Okay, so now there's a natural way to formulate the general version of the algorithm in non-Euclidean setups where the decision space is just a metric space, which is to say the following. So now, remember that in the previous version of the algorithm, the classical one, the measure MT was initialized to be a uniform distribution. Here we cannot, so we just take a prior distribution of K, and this will play a very important role. And then instead of taking XT to be the average of measure MT, we just take a barycenter of MT. Why not? We can define the subject here. And then the update is exactly the same as before. Because, I mean, here we're just looking at quality measures and the density is well defined, and no problem. Okay? So the main insight that I was kind of looking for, but I didn't know which form it was going to take, is that the performance of the algorithm actually depends on the geometry of something which is well known by geometers as something characterizing the geometry of a space, which is the fact that you're given a distance and a measure, and this leads to the study of so-called metric measure spaces. And so the the insight is that the performance of the algorithm depends on the geometry of this metric measure space, which is the decision space equipped with the distance that is naturally endowed with for the application you have in mind, and when the reference measure is the prior measure you choose.
Quentin, I'm very sorry, but the time is over. So
okay, so I will just stop with this statement that, which is an informal one, that supposing that all loss functions are geodesically beta x concave in the same sense than before, then we recover exactly the performance that we would expect in the Euclidean world, provided the metric measure space we're considering has a synthetic Ricci curvature lower bound, which I'm happy to talk about if you're interested. Thank you very much.
Okay, thank you very much. Dear colleagues, any questions? Ilya, you can ask.
Thank you very much. I was just asking if I can have a look through the presentation, because I was late from the beginning, and I would really like to start from the very beginning of the presentation.
Yeah, I'm happy to send my slides, no problem. So if you give me, I don't know, I can send it to your email or send it to Ivan, who can send it to you. No problem.
As far as I see, there are much more slides. Maybe you can just scroll them just for us to see what you was going to.
So I have three slides, ready to talk about, to give some details of what I mean by synthetic Ricci curvature lower bound, which is the so-called measure contraction property, which looks at the way if you take a set and you contract it along geodesics to points, and you look at measure of these contractions, how it behaves. So there's a general thing studied by geometers, which is called this measure contraction property that looks, that is this given by this definition. So it looks pretty awful, but actually it's extremely elegant when you dive into it, because this measure contraction property was actually shown by a Japanese researcher in 2007, Shinichi Ota, to be exactly equivalent to classical Ricci curvature lower bounds on Riemannian manifolds. So I can go in details about this if some of you want.
Okay, so some more questions, comments.
Yeah, I have a question. Oh, sorry.
Yeah. Please, Bruno.
So this picture with two dots on this, you associate them to probability measures. I didn't understand how you do it. You quickly said it, but I didn't.
So what you can do, it's a good question, because it's not straightforward actually. What you can say is that you can look at this square, okay, as giving you so either as a matrix, which is the obvious pixel type structure that you want to look at, or you can think of this object, the square. Sorry, let me take my pen. So you can look at this, okay, as being simply this actually encodes the graph of a function. So I'll define in 3D. Okay, so a function defined. This is the picture of a density, which is defined on 0, 1 to the square, taking values, positive values. Well, it's, just taking value 1 here, and so.
You get the density by smoothing out neighboring pixels or something.
So yeah. So here I'm looking at a smooth version, or you can, so I'm looking at the object without discretizing it now. In this case.
Okay, and then it's logical that the geodesic looks like this. Okay, I get it. Yeah.
Sergey Olegovich, please.
Thank you, Quentin, for the sparring talk. I would like to ask whether the techniques you described in the first part on the gradient descent in convex means, can it be naturally extended to non-convex cases.
To non-convex.
Yeah.
I mean, you can look at this in the non-convex world. The only problem will be to provide guarantees that it works. So this algorithm makes sense without convexity. Okay, so you would have to be careful because then projection is not guaranteed to be unique. And so suppose the decision space is RD. So in this case, you just forget about projection. Okay. There's a lot of work just in actually offline. So suppose that your classical you're doing just classical optimization with a fixed objective function. I mean, already for this problem, which is a simpler problem, in some sense, there's a lot of work and nothing totally conclusive about optimization of a non-convex function. There are some cases, I think, when I'm not a specialist of non-convex optimization, but I think it's already a problem when for a fixed function. There are probably people in the audience which are much more competent than I am on this question, but it's a not easy non-easy problem.
Thank you.
For the exponentially weighted average algorithm, you don't need K to be convex, or I mean you can.
Yes.
But did you assume K was? Sorry, you didn't assume K was convex. Okay, sorry.
I mean, so you still need convexity of K because the functions f have to be convex, and so to define convexity of the functions, they need to be defined on a convex set. Otherwise, it doesn't make sense. But so the loss functions have to be convex. They're defined on K. So K has to be convex for the definition of convexity of f to make sense.
But you can just have a requirement on any 2 points that are connected on the inside. You can weaken the definition of convex functions.
Well, but then now you're moving towards geodesic convexity, which is convexity along some lines which are between 2 points. But then it's a new geometry, so you're actually moving in the direction I want to move into. So
that's good.
Okay, any more remarks, corrections? If not, then let me thank Quentin for his very interesting and stimulating talks. I hope that people may work together, and this is our meeting as such place to find common interests. So, dear colleagues, thank you for being with us today. See you soon. Goodbye.